Hello students, hope you are having a great day. So we were discussing computer skill 2 for our university students of science background or maths background, and under that we have already discussed the number system, under which we have initially discussed the decimal and binary and octal and positional number systems, and now we come to the last number system that is important for this particular number system part of computer skill, which is hexadecimal number system. As the name suggests, hexadecimal means here 16. And the topic that we'll be covering is just the conversion of hexadecimal number to decimal, binary, as well as binary to hexadecimal, and to some extent we'll be discussing octal also, though it is not written in your syllabus. So coming to the hexadecimal number system, it is similar to the earlier things, only difference is that here n is equal to 16, and so here n to the power n is here, and the digits are here. This significant digit and the most significant digit last to first. And here the difference is that here we have changed this to HI instead of OI or BI or DI, and the digits obviously are 16 instead of 10 or 8 or 2. So coming here we will be converting first hexadecimal to decimal form. So as this n is equal to HIQI, so here I can be positive or negative. I'm not going to the negative part now, which we'll be discussing in the fractional analysis, which will be the last lecture of this number system. Now here hexadecimal decimal means base 16 to base 10. So in general, n is a real positive number in decimal, and what we do here is that h is varying from 0 to f. Why 0 to f? Because here we need 16 numbers, n is equal to 0 to n minus 1. So 0 is 0 and n minus 1 is 15. So we have the numbers 0 to 15, and we have the symbols for 0 to 9, but for 10 to 15 we have the same system repeating in our decimal. So in hexadecimal they become 10 becomes A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, and finally 15 becomes F. So here, just similar to your binary or the octal or decimal, here it is 16 to the power 0, 16 to the power 1, 16 to the power 2, 16 to the 3, and so on. So obviously the values are high. 16 to the power 0, like all others, is 1. But here 16 to the power 16, 16 square is 256, and 16 cube is 4096. As you go on here, we may have much higher values, which are not going for the complexity of calculations. Now let us consider a number which is 18CF. Now this C and F is actually, C means if A is 10, B is 11, C is 12, and F is 15. So 1 into 4096, 8 into 256, C is 12, so 12 into 16, and F is 15, so 15 into 1. So 18CF is nothing but 6351 half. This is the way 16 into 3, so 4096 plus 2048 plus 192 plus 15 equal to 615. So this is how we convert a hexadecimal number to decimal. Now let's go to the more simpler one, hexadecimal to binary. We know that hexadecimal numbers is one number system which has 16 values, and those 16 values are 16 different symbols. 0 to 9 is as decimal have 0 to 9. We are accustomed to 0 to 9, but after 10 we are repeating with 1 and 0, 1 and 1, 1 and 2. So these are a new set of symbols: A, B, C, D, E, F, the alphabet, first 6 alphabets, which are being used as the new symbols. Now next we go to this, where we know that 16 is equal to 2 to the power 4. So one hexadecimal number is actually equal to 4-bit binary number. So if we see 0 to base 16 to 0 base 7, 0 base 16 to 7 base 16 are actually binary numbers 0000 to 0111. In the next set, 8 base 16 to 15 base 10, which is equal to F base 16. So you can see here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 base 10 is equal to A base 16, 11 base 10 is equal to B base 16, 12 base 10 is C base 16, and so on. And we have the binary numbers. Only difference in these two lines is that the first digit is 1 and 0, and the next digits are same. So to convert a hexadecimal number F1 base 60 into binary, what we have to do is that F is equal to 111. As for this table, 15 means 1111, and 1 is equal to 001. You can see here. So these two come here, and this F1 is very simply equal to 1101. So let's check it whether it is correct or not. So 15 into 16, 15 means F, and 16 to the power 1 plus 1 into this is equal to 240 plus 1 is 241. And if you take this binary number, this 1111, so it is 11100001. So here what we have, 2 to the power 0, 1, 2, 3, 4, 5, 6, 7, and 7 is 128, 6 is 64, 5 is 32, 4 is 16, 8 but multiplied by 0 so 0, 4 by multiplied by 0 is 0, 0 multiplied by 2 is 0, and 1 as it is equal to 241. So what is the common thing? You can see this 241 and this was the 241. So F1 is simply this. So what we have to do is that take each and every hexadecimal number digit and convert it to 4-bit binary once you change the base from 16 to 2. Let's try a few examples. Hexadecimal number is 1AC5, 1 is 0001, A is 10, so 1010, C is 12, so 1100, 5 is 0101. But here we have to remember that 1 and 5, though they are only 1-bit or 3-bit numbers, we have to remember that all of them have to be converted to 4 bits. So that's why instead of 101 we are having 0101, and instead of 1 we are having 0001. So when you put them together, this is the binary number. Another example, 3AB2, so 3A, B, and 2 together is this. So what we are actually doing is that 9AF is nothing but these 3 digits, and we club them together and become binary. So it's very easy to do that. But there is a long process also, and that is the indirect conversion of hexadecimal to binary. What is that? This is the layman method. So for example, you don't know this technique, how will you do that? This is the easy technique, but many people, if they do not know, they go by the old layman way, where it is a two-step process. We take a hexadecimal number, convert it to equivalent decimal number, and take the decimal number, convert it to a binary number. This is a lengthy process. We normally do not go for it. Still, as it is also a process, we'll be discussing it. So F1 is 15 into 6. This is 241. And how to do that? For decimal to binary, we go for successive divisions. 2 by 241, 120 remainder 1, 60 remainder 0, 30 remainder 0, 15 remainder 0, 7 remainder 1, 3 remainder 1, 1 remainder 1, and the last one is 0 remainder 1. So this is the MSB, this is the LSB. You write it down. So this is how F1 is taken, converted to 241, and this 241 is converted to 11110001, with this being the NSB and this being the LSB. So for conversion, the vice versa, binary to hexadecimal is a reverse process. It is just to reverse the earlier first process of direct conversion. 2 to the power 4 equal to 16. So 4 binary bits have to be now converted to hexadecimal. The steps are very simple. Take the binary number, divide the binary number into groups of 4, starting from right for the integer part. Start from left for the fraction part, which we'll be discussing later. Convert each to 4 digits to one hexadecimal digit. So it's just the reverse process. Earlier we had N16 on the top and N2 on the bottom. Now we are writing it the other way around. So it's the same thing. So if this is a number, binary number, take 4, 0, next 4, 1, next 4, 7, and next 4, 0. You can do it in this way also. So binary digits, group of 4, hexadecimal each groups of number. So just grouping starting from the right, divided into blocks of 4. So we have done a lot of examples in this way. So hexadecimal can be converted to octal and octal to hexadecimal via the binary numbers. Because we know that octal to binary there is a relation to the power 3 equal to 8 and to the power 4 equal to hexadecimal. So we can use this relationship for the interconversions. How? Hexadecimal convert to binary, convert to octal. Because hexadecimal to binary is easy, binary to octal is easy. You can see here 1AC is 1 is 0001, A is 1010, C is 1100. This is the binary number. Now instead of group of 4, we make it group of 3 for octal. 2 to the power 3, this is 2 to the power 4. 100 is 4, 101 is 5, this is this, 10652. The reverse is also possible when you want to convert octal to hexadecimal. 175 base 8 is the octal number. You take the binary conversion, 5 is 101, 7 is 111, 1 is 001. Group them in the group of 4 instead of group of 3. Convert them into decimal, hexadecimal. So like this, 175 base 8 is equal to 7D, or 1AC base 16 is equal to 0654 base 8. So we have done a lot of number conversions, binary to other number systems like binary to decimal, binary to octal, binary to hexadecimal, decimal to number systems, binary, octal, and hexadecimal, octal to binary, octal to decimal, and octal to hexadecimal, and obviously the last one, hexadecimal to the other numbers. So thank you for your patience. We have discussed the main four, that is binary, decimal, hexadecimal, and octal number systems, where decimal is the core because we are accustomed to the decimal number system, whereas our computers prefer hexadecimal, and some earlier 8-bit systems prefer octal, and the binary number system is the core and the base of the whole thing because our computers understand on or off or 0 or 1 only. So we'll be discussing the fraction part and the floating point part in the next lecture. Till then, I would like to stop here and wishing you all the best. Thank you very much. Thank you for your patience. The last lecture of the number system will be related with fractions. So bye for now.